Take a look at our EMR unit assignment. We're starting with question number 1. Accelerating charges generate, listen, the very first day of this unit, we talked about 3 keywords, right? The whole EMR production and propagation and what it consists of boils down to 3 words. You guys remember what those 3 words were? Accelerating, right? What was the second word? Somebody said it. I heard somebody say there. Changing, yeah. And the third word was perpendicular. Remember those 3 words. Those are going to help you on tomorrow's test. I promise you that. Accelerating charged particles generate changing electric and changing magnetic fields. It's important to have changing electric and changing magnetic, right? Not just constant, because we need an electric to produce a magnetic, and we need a magnetic to produce an electric. And that doesn't happen if they're constant fields. They need to be changing. So accelerating charges generate changing electric and changing magnetic fields that are perpendicular to each other. One's on the y-axis, one's on the x-axis, and perpendicular to the direction of propagation. So one's on y, one's on x, and they're going to propagate on the z-axis, or whatever the case may be. All right, let's look at question number 1 again, keeping in mind those 3 key words that are really going to guide us to the answer number 1 and number 2 for that matter. Accelerating charges generate changing electric and changing magnetic fields that are perpendicular to each other and perpendicular to the direction of propagation of the waves. Accelerating charges generate, the answer is D, electromagnetic radiation, right? Accelerating charges generate electromagnetic radiation. Do they generate electric waves and magnetic field? I suppose they generate electric and magnetic waves, but more specifically, changing electric and changing magnetic waves, which, what do we call that when they're changing electric and changing magnetic field waves? We call it electromagnetic radiation. So the best answer there is D. Maxwell proposed the theory that an oscillating electric field, a changing electric field, generates a changing magnetic field. Be careful here, because D is tempting a perpendicular electric charge. If it's a perpendicular electric field, that would be correct, right? Sorry, no, that wouldn't be correct. An oscillating electric field would generate a changing magnetic field, not a changing electric field. This is already your changing electric field. So it would generate a changing magnetic field or a perpendicular magnetic field, but not a perpendicular electric field. So C has to be our answer there. Next question, number 3. Selected regions of the EM spectrum. We've got a bunch of them here. You want to rank them in terms of increasing wavelength. Listen, details, right? Details, increasing wavelength. It is so tempting to say, oh, I've learned these radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Yeah, that's right. If you're talking about increasing frequency, if you're talking about increasing wavelength, then you're going in reverse, right? It's decreasing frequency. And just like trying to recite the alphabet backwards, which is almost impossible, without writing it down and then reading it backwards, like seriously, try it. A, B, C, D, E, F, G, everybody can do that, right? Oh. Say the alphabet backwards. We can't, right? Like we can't. So if we have to recite it backwards, it's useful to write it down, to write down the alphabet and read it backwards. That's exactly what we want to do here. If we're talking about wavelength, ranking it in terms of wavelength, then write it down in terms of frequency and then just read it off in terms of wavelength. So what I like to do is start off with visible light, which consists of red, orange, yellow, green, blue, indigo, and violet. And then below red, we have infrared. Above violet, we have ultraviolet. And then below infrared, we have radio waves and microwaves. And then we have above ultraviolet, X-rays, and gamma rays. So increasing wavelength, we're going this way. It's so tempting to go the other way because we often see it as increasing frequency. That's the way we did it, was increasing frequency. So increasing wavelength is decreasing frequency. Gamma is going to be the lowest wavelength. Looks like gamma is the lowest wavelength. Looks like our answer is going to be A or C right away, right? The only 2 that start with gamma rays, the lowest wavelength. What do we have next? X-rays? Well, X-rays doesn't even appear on here anywhere. Next one is ultraviolet. Okay, that would be number 4. Looks like our answer has to be C. All right. Well, let's just keep going just to make sure here, okay? What do you have the next? Visible light. Yeah, that works, right? 5, visible light. And then we're down to television and AM radio. These are both radio waves. Now, which one comes first? It's like Roy G. Biv, right? Different ranges of frequencies within visible light. Well, these are different ranges of frequencies within radio waves. But you don't need to know different bands of frequencies within radio waves. So how are you supposed to answer that? Well, you don't have to, right? You don't have to, because you get to this point and you don't have to distinguish. You just have to know that those are both radio waves and they're both going to fall last. One's going to fall last, one's going to fall second to last. Which one's which? You only have one option, 1 and 2. Now, 3, 4, 5, 1, 2 is our correct answer. If you had another option, 3, 4, 5, 2, 1, that wouldn't be fair, because that would require you to know whether television or AM radio came first on the spectrum, and you're not expected to know which one comes first. Roy G. Biv with invisible light, absolutely. But radio waves, AM radio waves in TV, you're not expected to know which one comes first there. All right, good there? All right, so our answer is C. Numeric response number 1, if certain X-rays have a frequency of this, then what's the period? Pretty straightforward question, right? But it's important that we know all of the equations that apply, and it's important that we know all the variables, what all those variables mean as well. This is very straightforward if you just recognize that period is 1 over frequency. And if you don't recognize that, well, then you got a little bit of work to do before tomorrow, right? Because that's a pretty basic thing, and we have to know that. The frequency is 2.15 times 10 to the 20. So let's go 1 over that. We do that, we get a value of the frequency, the period of 4.65 times 10 to the minus. I'm not sure what that exponent is because I didn't write it down. But as it turns out, we don't need to know that either, right? Because it just says B times 10 to the W. What's the value of B? 4.65. We often see the A, B, C, D ones where we have to express the exponent. If we did, we'd fully calculate that and express the exponent, but we don't need that there in this question. Next one, fiber optic cables. Was it 3 or 4 years ago? They TELUS dug up Okotoks and put fiber optic cables all through Okotoks to speed up internet, to give us crazy high speed. Get gigabit internet now, which is crazy fast compared to what we had, what we had before. And that is largely due to what's carrying the information. Radio waves carry information, right? When you talk on your cell phones, microwaves carry information. So you get data encoded in microwaves. Well, here we're embedding data or encoding data in visible light. Visible light is traveling through these little glass cables. And the visible light is carrying this information, it's carrying this data, reflects off of the boundary between the glass and the air. Glass, which we're told has an index of refraction of 1.51, and air, which has an index of refraction of 1.00. Not going to reflect the other way, right? You couldn't have an air cable surrounded by glass because you wouldn't get total internal reflection there. Reflection has to happen from high to low index of refraction, 1.51 to 1. And you have to be above the critical angle. What do we got here? We're looking for the critical angle here. You guys know that when you're looking for critical angle, you're going to set theta 1 equal to that critical angle, and theta 2 will be 90 degrees. When looking for the critical angle, it's always N2 over N1 is equal to sine theta 1 over sine theta 2. But theta 1 is theta C. And theta 2 is 90 degrees. So sine 90 is 1. So this just disappears. In fact, for a critical angle problem, you don't even need to write that down on the bottom if you don't want. Be careful though. If it's just a regular Snell's law problem, not critical angle, you need the sine theta 1 over sine theta 2. Just not here, because it disappears. N2 is 1.00 and 1 is 1.51 equals sine theta C. So we're going to first of all check our calculators, make sure we're in degree mode. Sine 90 is 1. We are good. Then we're going to take the second function or inverse sine of 1 over 1.51. The good news is if you mess up those indices of refraction, get them backwards, what happens? Error on your calculator. That does not happen with other Snell's law problems, but it does happen with critical angle problems if you mix up the indices of refraction. So that gives us a value of 41.5 degrees. 41.5 degrees. Yeah, we just express it as 3 digits, not scientific notation. 41.5 degrees. You guys remember we talked about this when we went through the diamond and how the diamond reflected light. We said the bigger the difference in indices of refraction, like here the difference is 0.51. We're going from 1 to 1.51. The difference is 0.51. The bigger the difference in index of refraction, the smaller the critical angle. So this is not a massive difference in index. That gives us a critical angle that's actually fairly big. If we used a material that had an index of refraction of 1.8, let's say, 1 and 1.8, the critical angle would go down. The critical angle would go down. So I think I told you guys, did I tell you guys about my wife's eyeglasses? How strong they are? I think I did, yeah. Her eyeglasses, to make her lenses reasonably thin, have a really high index of refraction. Higher, I have high index lenses, but her index is even higher than mine. That results in her lenses being thinner, which is a good thing, and being a lot lighter. But it also results in sometimes some glare that the rest of us might not see. She has a hard time driving at night sometimes, and part of that is because of glare on the glasses. Because there's such a difference in the index of refraction between air and her glasses, there's more likely to get the critical angles lower, and there's more likely the total internal reflection taking place within her lenses than there is within my lenses or within Sam's lenses. Does that make sense? Now, Johnny isn't wearing glasses at all. He's not going to get any glare. I'm going to get more glare than he is because total internal reflection can happen within my glasses, but because the index of refraction difference between air and my glasses is lower than it is between air and my wife's glasses, the critical angle is bigger. The bigger the difference in index, the smaller the critical angle, and the more likely reflection is to take place. All right, next question. A ray of light traveling from water into an unknown medium is shown below. I've given you the angles here. The original form of this question actually did not give you the angles. You were required in the original form to measure the angles with a protractor. Last year, when I gave this question, I made people measure the angles for this. The reason I didn't make you guys is because, well, last year when we did this, we did a lab on Snell's law where you were required to use protractors to measure angles. This year, what did we do? Well, when we did that, you guys were at home and we did a simulation, right? Which you guys had to use a protractor for, but not a real protractor. So I didn't think it was fair to make you guys use a real protractor. You guys will not have to use a real protractor for your test or for your final exam. Yeah, I won't make you do that because you didn't have that skill from a lab that we usually do in class. I gave you the angles here. And what are we looking for? The index of refraction in the second medium. Look, this is going to be theta 1. This is going to be theta 2. We're told that N1, water index of refraction, is 1.33, and we're looking for N2, the index of refraction in the unknown medium. So let's say N2 over N1 is equal to sine theta 1 over sine theta 2. Be familiar with this equation. Know where to find it. Know what each of the variables mean. N2 is what we're looking for. I like it when what we're looking for is on the top. It makes it easier, I think, at least. It makes it easier. And 1 is 1.33. Sine 39 degrees over sine 32 degrees. I've already checked my calculator to make sure I'm in degree mode. Tomorrow, your calculators will be cleared. they will automatically go back to radian mode. You're going to want to switch those to degree mode. And then before you do a calculation with an angle, do sine 90 just to make sure that you did switch it back to degree mode. Okay, I'm in degree mode here, good. So I'm going to go sine 39. Now watch this. This morning, I went sine 39. By accident, I did this, not on purpose. Sine 39 divided by sine 32. And then I multiplied it by 1.33. Got the wrong answer. What did I do wrong here? Yeah, I got to close the bracket around the 39 and around the 32. Okay, so what this does is say 39 divided by sine 32 is a number. And then I'm taking sine of that number. That's not what I want to do. I want to say sine of 39, whatever that is, divided by sine of 32, whatever that is. That gives me 1.18. Let's multiply that by 1.33 because the 1.33 goes up by multiplying. And that gives me a value of 1.579, which we round to 3 digits. So it becomes 1.5. Okay? And no scientific notation there, just a number, 1.58. 4, an object is placed 35 centimeters from a diverging lens. Remember, details, for heaven's sakes, you guys. Sometimes people don't trust me on things like this. When I say, like, pay attention to details, circle this, always, what type of lens or what type of mirror it is. People don't trust me because people think that, you know, listen, I've been doing this course for 4 months. Okay, I'm 18 years old and I've been doing this course for 4 months. Guess what? I'm 49 years old and I've been doing this course for 26 years. Trust me. You are better off if you follow my advice. And I'm telling you, when you see what type of lens it is or what type of mirror it is, circle that. When it's diverging, what does that tell us? That it's a negative focal point. Okay, make a note of that. Like little things like that help you. Trust me, they help you. Okay, so we're told the focal length is it's 20 centimeters. I'm going to say F is equal to negative 20 centimeters. I'm going to write that down right now. Okay, now I'm not going to mess up on that. Now, as it turns out, I suspect that some of you didn't even do any math for this question. I didn't actually. I used my ray diagrams / patterns. How many of you guys did that? Ray diagram / pattern. That's the way I like for this method, but the math works too. How many of you guys did math? About half. Okay. About half and half. Guys, let's look at the ray diagram / pattern first. This is a diverging lens. If you remember the patterns, diverging anything, lens or mirror, always produces an image that is smaller, that is upright, and that is virtual. So the answer has to be D, just from our patterns. Now, if you wanted to sketch the ray diagram, here's my diverging lens. It doesn't matter where I put my object, but I'll put it, like this is 20 centimeters, this would be 40, so I'll put it in between. It doesn't matter though, because the image is always the same. First ray diverges from the focal point down through the optical center, and that gives me an image right here that is smaller, upright, and virtual. So A, remember the pattern, gives you D. B, draw a ray diagram, gives you D. Or C, you can do the math, which half of you did. And I'm not surprised. Usually it's more than half, actually, does the math. We would say DO is 35 for this. We would say F is negative 20. You can see how important that negative is now. I might as well solve for DI here. DI, let's say 1 over F is equal to 1 over DO plus 1 over DI. 1 over negative 20 equals 1 over 35 plus 1 over DI. Now, on our calculator, we're going to say 20, 1 over 20. Sorry, that's wrong. 1 over negative 20. Easy to make a mistake like that, right? Be careful. Check your work. Be Be conscious of everything you do. Now, 1 over 35 goes over by subtracting. What is going on here? There we are. I think I'm good there now. There we go. Subtract 1 over 35. Now we're going to flip that over. Gives me a value of negative 12.7273. What does the negative DI tell me? The image is virtual. It's an image subscript, DI, right? So the image is something. Remember F, DO, and DI? Negative meant virtual, positive meant real. M, HI, and HO, negative meant inverted or upside down. So this is virtual. So that means the answer would have to be C or D. Now, to determine that it's smaller, probably going to want to do the magnification here. Negative DI over DO. I get negative 12.7 over DO, which is 35. I don't know what that number is. Somewhere around 0.3. It's a number that's less than 1, right? And if it's less than 1, it tells us it's smaller. Yeah, it's smaller. So sure enough, the answer is D. Any way you want to do it. Feel free to stop me, guys, if you need me to spend more time on a particular question. 4, numeric response 4. In an experiment similar to Young's double slit experiments, the student measured the distance between the first antinode and the fourth node. Watch that too. And don't make a mistake because you just don't read it carefully. The first antinode and the fourth node, and they're both on the same side, so it's not on opposite sides of the central max. That distance is 9 millimeters. The student set the screen 3 meters. Watch those units, meters and millimeters. Slits were separated by 0.5 millimeters. Let's draw this out, hey? Here's the slit spacing, which, by the way, the slits were separated by 0.5 millimeters. That's D. Make sense? All right. What else we got here? The screen is 3 meters away, so that's going to be L. That's going to be L. And first antinode and fourth node, central bright spot, central antinode or bright spot, first order antinode, second order antinode, third order antinode, fourth order antinode, and of course it goes on the other side as well. We don't need to draw those though. First antinode and fourth node. 1, 2, 3, fourth node. That X value in between the first antinode and the fourth node is 9 millimeters, although we want to convert that to meters. What's N going to be there? First antinode, fourth node. N is 2.5. 3.5 minus 1 is 2.5. All right, we should be good now. Let's say lambda is equal to XD over N times L. X is 9 times 10 to the minus 3 meters, right? Not 9 millimeters, 9 times 10 to the minus 3 meters, times L, times D, I should say, which is 0.5 times 10 to the minus 3, divided by N times L. Use brackets on the bottom because you're doing an operation in the denominator there. So let's do this now. 9 times 10 to the minus 3 times 0.5 times 10 to the minus 3 divided by brackets on the bottom. 2.5 times 3 gives me a value of 6 times 10 to the minus 7. Okay, so we fill in 6007, correct? Oh, what a trick here, eh? Not quite a trick, because the original form of this question just said the frequency of EMR, and it didn't have frequency italicized. I don't know, it's a year and a half of a pandemic, get a little soft, and I decide to italicize the word frequency to remind you that you're not looking for wavelength. Because man, the temptation is to find wavelength here and be done, right? So be careful of that. Okay? I don't remember exactly what the test looks like tomorrow in terms of a question like this. There's a question on here on this stuff for sure, but I don't remember if it asks for wavelength or frequency. If it asks for frequency, usually it's not italicized. I did that for you here to point that out, but on a test, it probably wouldn't be italicized. So how do we get the frequency from that? V over lambda, right? 3 times 10 to the 8 divided by 6 times 10 to the minus 7. And it gives me, I believe it's 5.0 times 10 to the 14. So 5014 would be my answer there. Hey, when I get 5 times 10 to the 14, I'm fairly comfortable with that. Because 10 to the 14 is visible light. And we're not always using visible light here, but often we're using visible light. So no guarantees, but pretty comfortable with my answer there. All right, number 5, multiple choice number 5. When a girl who is 122 centimeters tall stands 40 centimeters in front of a mirror, DO is 40. We don't know what type of mirror it is this time, so there's nothing to circle there. Her virtual image, okay, I am going to draw attention to that. Her virtual image, that makes DI negative. Now, I'm not sure if that's going to help me that I recognize that, but I recognize it, so might as well write it down just in case. Her image is upright and 54 centimeters tall, so we'll make HI positive 54 centimeters. We want to find out where the image is located. We want to find DI. Then we want to find out what type of mirror we have. If you're going to do this with a calculation, to find the type of mirror, DI is not going to tell me what type of mirror it is. F is going to tell me what type of mirror it is. Positive F versus negative F. Okay, so let's find DI first. So HI over HO equals negative DI over DO. That's the magnification equation, right? HI, 54 over 122. So what are we going to do? Say 54 divided by, oh, you know what? Let's say 54 times 40. That was a great band in the 90s, 5440. You ever heard of 5440? No, look it up. It was a good band. Sorry, I've never heard of what? No, that's true. Yeah, that's true. So we're even, I guess, now. 54 times 40, and then let's divide that by 122. Or you could have said 54 divided by 122, and then multiply the whole thing by 40. You'd have to use brackets, though. Okay. 17. That's actually negative 17, right? Because the negative on the DI. Negative 17.705. So that means the answer is either going to be A or C, right? A or C. Now let's find F. Some of you might look at this and say, look, the image is smaller, and the only time we get a smaller virtual image is if it's diverging, a diverging lens or mirror. That would be enough to tell us convex is diverging, right? That'd be enough to tell us the answer is A, whether patterns or ray diagrams. But if you didn't remember that, that's fine. Just solve for F. 1 over F is equal to 1 over DO plus 1 over DI. 1 over F is equal to 1 over 40 plus 1 over negative 17.705. Now, we should get a negative F, right? A negative focal point telling us that it is a convex mirror or diverging mirror. Remember, convex is diverging from mirrors. Convex is converging for lenses. Remember the difference there. Man, all these little things to remember here. So let's say 1 over 40. Let's add 1 over negative 17. Or you could just subtract 1 over positive 17. Put that over. Negative 30. I don't even care what the number is, except that it's negative, right? A negative F tells me it is diverging something. Diverging lens, diverging mirror. If it's a mirror, it's convex. Whew. Getting there. Classical wave theory, also known as wrong. And quantum physics or photon theory, quantum physics, also known as right. Make different predictions about the effect of incident EMR on the photoelectric surface. Here's the 4 predictions. And we want to know which ones are quantum theory and which ones are classical wave theory. In other words, which ones are right, which ones are wrong. Number 1, low intensity. What does that mean, low intensity? If I have low intensity versus high intensity, it means I have less photons. Less photons. So less photons a low number of photons here. Oh, but we got a low number of photons for a long period of time. Nothing's happening, nothing's happening, nothing's happening. And then all of a sudden something happens? No, if it doesn't happen immediately, it will never happen, right? Doesn't matter how many you have. If it doesn't happen immediately, it must mean you're below the threshold frequency. Nothing happens ever. So that would be wrong. This one would be classical theory. High intensity. This is a high number of photons. Lots of photons will not cause emission unless the frequency is greater than the threshold frequency. Is that true? Yeah, that's a correct statement. So therefore it must be quantum. The energy of the emitted electrons will increase if the intensity or the number of photons of the EMR increases. The energy of each electron will increase if you have more photons. Is that true? No. The energy of the electron and the number of photons is irrelevant. Number of photons goes with number of electrons. The energy of photons or the frequency of photons goes with the energy of electrons. So that's an incorrect statement. We will say that that's classical theory. That must mean that this is quantum, but let's just double check it. The energy of the electrons is not related to the number of photons. Is that correct? Is the energy related to the number of photons? No. So the energy is not related to the number of photons. That's a correct statement. So therefore that is quantum theory. So sure enough, 1324 is our answer there. Don't you hate that when you got to do a question like this where you got to basically answer 4 questions? You only get 1 point for it. I know, like, for me, when I see something like this, I'm like, geez, if I'm going to get this one wrong, I might as well get all 4 of them wrong. At least make it worthwhile, right? At least make it worthwhile. I always say that, like, don't, seriously, to some degree, like, I mean, I'm being a little bit facetious here, but you don't want to make some little mistake. Like, you're going to make mistakes, but at least make it a worthwhile mistake. Don't make it some silly little mistake. Like, if you're going to get it wrong, just butcher it. You might as well get it out of your system, and then work on the next question. Right? Don't make some silly little mistake. All right, next one. Numeric response number 6. You're going to get one of these for sure on tomorrow's test and on your final exam too. Nice thing about these, they're all the same. Get this right tomorrow, please. Get this right. There's no tricks to it. It's just like this question. 2 equations, always. D equals d over t, t1/8, the time for 1/8 of a rotation, or the time that it takes the light to go there and back. Period 1, time for 1 complete rotation. Looking for the speed. Distance is 70,000 meters. 35 times 2, but in meters. All right, nothing. T1, don't know, but we know the frequency. 1 over 500, 0.002. You guys remember what I said you get? A time that you don't want. How do you get the time that you want? I got big T, I need a little TI. Yeah, divide by 8. Divide by 8. That gives us a little t of, what was that, 2.5? 2.5 times 10 to the minus 4. Take that number, sub it in here, 70,000 divided by 2.5 times 10 to the minus 4 gives me 2.80 times 10 to the 8. 2808. If I get 2.8 times 10 to the 8, that's pretty close to 3 times 10 to the 8, right? How comfortable can I be? Yeah, not 100%, but fairly comfortable in that answer, right? If I get 2.4 times 10 to the 22, how comfortable can I be? Not at all. Right? You're pretty sure you're wrong there. I see somebody laughing over there. I hope you didn't get 2.4 times 10 to the 22.
No, 26.
10 to 26? Yeah.
You don't need.
Yeah. It's always the struggle, hey? A group of students, and this is a good question. This is a hard question, though. I think that this might be the hardest question on the assignment, but it's a good one. A group of students investigates interference patterns. The students use a green diode laser to direct green laser light on a diffraction grating onto a ruler placed at a distance behind the diffraction grating. So this ruler is basically our screen, right? The students adjust the position of the ruler until the central maximum is at the 0 position. So this is the central maximum, first order maximum, second order maximum. And then we have 2 trials here. First trial, we'll replace the green diode with red. So what are we doing here? We are if we're going from green to red, frequency is going down, green to red, or wavelength is going up. So we're increasing the wavelength. That's what we're doing there, right? Increasing wavelength. In the second one, it says, replace the diffraction grating with one whose lines are closer together. So the openings are closer together. That means for this one, we're making D smaller. The spacing of the slits is smaller. And we're going back to green. We're going back to my original diagram, the original up there, okay? Let's look at trial 1. What happens in trial 1? Remember we said a number of times, if you're looking to find a relationship between variables, that's really what we're doing there. Write down an equation. I'm going to say lambda is equal to xd over n times L. Now, look at all these diagrams. What are they really showing me? They're showing me the distance between the maxima. They're showing me x. So let's rearrange the solve for x. We want to find the effect on x. If we want to find the effect on x, well, this is the one that you guys were debating, isn't it?
Yes.
Yeah. We want to find, and I haven't released your marks yet, have I? No. So you don't know whether you got this right. Oh, the mystery. We want to find the effect on x. Solve for x. X is equal to lambda times n times L goes up over D. What am I doing in trial 1? We are increasing lambda. If I increase lambda, x goes up. So that must mean that the dots, the maxima, are going to be further apart. They were 0 to 13. 0 to 13. X was 13. So we need a number that's bigger than 13, correct? Well, 11 is not bigger than 13, but 15 is. So that means the answer is either going to be A or B. X goes up for A and B. X goes down for C and D. Now let's go to trial 2. Back to green, back to my original diagram. Now what are we doing? We are decreasing D. As D goes down, X goes up. So what was X on my original diagram again? 13-ish. X has got to be bigger than 13, which means, well, C and D don't work because that's like 7, right? X is equal to 7 there. Sorry, A and C don't work. A and C don't work. B and C do work because X is 20 as opposed to 13. So the ones that overlap, of course, is B. Get it right?
Yes.
Good. Good for you guys. It's a hard question. Listen, guys, this one tests you a little bit on diffraction interference, but the main thing with this is not diffraction interference. It's the skill of how one variable affects another. You have to interpret that in the context of diffraction interference. But that skill we've seen a number of times throughout all of the units, right? How does one variable affect another? Get an equation and rearrange for the variable that you're trying to find the effect on. What happens to X? Get an equation and solve for X. Got it? And do what we just did there. A tough question though. Glad that some of you got it right. Good. And not by guessing. That's good. 7. Photon has a frequency, kinetic energy of this work function here. Let's write down some givens here. Frequency is 7.2. The kinetic energy of the electron is 1.00 eV. We're looking for the work function. Do we need to convert this to joules? Can we? Sure, we can always we can. Do we need to? No. Unless I'm using 1 half mv squared or QV, I don't have to. I'm going to go with that 5-second equation. EK max, but I get lazy sometimes. Use the 4.14 value because it's the electron volts. And the work function here is 1. Get this number and then take this number over by subtract, right? Subtract. And when I do, I think I get 1.98. I know I get 1.98 electron volts. If you did this in joules, that's fine, but you'd have to convert back to the electron volts at the end. A little bit extra work, but always works. 8. Satellite in orbit around Earth is exposed to radiation from the sun. This radiation may cause the satellite to become positively charged. This is the photoelectric effect. When light strikes a metal, if the electrons are ejected, the metal becomes positive. It loses electrons, it becomes positive. Here's the work function. We want to find which wavelengths will cause the electrons to be ejected. All right, we did questions like this, just like this on our worksheet, just not in a context like this. There's 2 options for this. We'll call it the blue option and the green option. See how many people did it each way. Here's the work function. I can say the work function is HC over lambda max. And I can rearrange that to solve for lambda max, HC over W. And I'm not sure what I get there. But whatever it is, it's a number, right? If I get lambda max, then that must mean in order to cause the electrons to be ejected, my wavelength must be below that number, below lambda max, above the threshold frequency, below the threshold wavelength. So whatever number that is, I'm looking for wavelengths that are below the threshold wavelength. So I want lambda to be below lambda max. Okay, when I do that, I would find that wavelengths 1 and 2 are below the maximum wavelength. So my answer would be A for that. How many people did it that way? Sorry, yeah, you're right. Thank you. How many people did it that way? Hey, good. That's the way that I probably would do it because it's a little bit quicker. The other way is just as good, but just not quite as quick. The other way is to say, look, I could calculate the energy of all of these. I don't know what each of them are. Calculate the energy of all of them. And we need our energy to be above the work function. If it is, then electrons will be ejected, right? Which ones do we find the energy is above the work function? Go figure. How many people did it that way? It's about 4 times the amount of work, right? So what? If it's right, so what? Right? Do it whatever way makes the most sense to you. All right, number 9. Oh, I like this. I like this one too. There's a lot of questions I like. I should have saved these for the test. EMR of constant wavelength. So we're not changing the wavelength here. We're incident upon a metal cathode, and the photoelectric effect is observed. So electrons are ejected. Which of the following graphs represents the relationship between kinetic energy and the number of photons? Our little physics thesaurus. Intensity means number of photons. What is the relationship? Don't even look at the graphs. Just tell me, what is the relationship between number of photons and energy of the electrons? How does the number of photons affect the energy of the electrons? Pardon me? It doesn't. The number of photons affects the number of electrons. The energy or the frequency of the photons affects the energy of the electrons. So if there is no relationship, what's my answer here? Correct. There is no relationship, the answer is A. Intensity changes, kinetic energy doesn't. Hey, here's one for you though. Here's a little side question, okay? Oh man, we're way ahead here. I just noticed there's only 2 questions left. Let's go back and spend another 5 minutes on each of these. One little aside to this here, okay, guys? Let me just change the question a little bit. What if it said, which of the following graphs represents the relationship between kinetic energy of the electrons and the frequency of the photons? What would be my best answer there? Frequency of photons is related to the energy of photons, right? So how does the energy of a photon affect the energy of the electron? What's the best answer? B would be the best answer. That B actually wouldn't be a correct answer, but it's the best answer. Here's what it would actually look like. The kinetic energy of the photons, the frequency of the photon, it would actually look like this, a linear relationship, but with an intercept. Anybody tell me why? Yeah, exactly. Like, if this was frequency instead of intensity, a frequency like of basically 0 does not cause electrons to be ejected, right? Hey, frequency of this, what happens? Nothing. Frequency of this, what happens? Nothing. Frequency of this, oh, something starts happening. This would be, what variable would that be? That would be my threshold frequency, right? So we couldn't change that question without changing that possibility, but B would be close for EK versus F. It's not quite correct. And 2 more questions that should go pretty quick for us. The Compton experiment was significant in that it demonstrates that photons have, remember Compton effect, light strikes metal, electrons ejected, second less energetic photon is ejected. And remember Compton explained that? He said, oh, it's a collision, like 2 trucks colliding at an intersection. But if you analyze a collision, you must use conservation of momentum. And if you're using conservation of momentum, collision of a photon and an electron, that must mean, and this was the big takeaway from yesterday, it must mean that photons have momentum. Do photons have wave properties? Absolutely they do. That's a correct statement. Well, no, it's not, because the Compton effect doesn't demonstrate that. Photons do have wave properties, but that has nothing to do with the Compton effect. Do they have a speed of 3 times 10 to the 8? Yes, but that's not demonstrated by the Compton effect. Do photons have mass? Well, no, they don't. So they do have momentum, they do have wave properties, they do have a speed of 3 times 10 to the 8, but this is what Compton told us, that photons have momentum. And lastly, Louis de Broglie Louis de Broglie proposed a hypothesis that was related to which of the following statements? What did he say? Remember, I said yesterday, really remember two things from this. If waves can have particle properties, then particles can have wave properties. And evidence came from electron diffraction experiments. You don't need that second part for this question, but you might down the road. Particles can have wave properties, and evidence comes from electron diffraction experiments. Okay, let's look at what option is closest to one of those two things. De Broglie proposed a hypothesis that was related to which of the following statements? The energy is the same as the energy released by the atom. No, he didn't say anything about that. If light has particle properties, then particles may have wave properties. That sounds pretty good. Let's just make sure now. C, the intensity controls the current in the photoelectric effect. Is that a correct statement? The number of photons controls the number of electrons? Sure, but that had nothing to do with de Broglie, right? That was an Einstein thing, not a de Broglie thing. And energy and mass are related. Are they related? Yes. But is that what de Broglie said? No, again, Einstein said that. So the answer is B. We thought it was B. Sure enough, it's B. Oh.